from mine, and it was my good fortune to be able to give them telescope time that enabled them to do this, because in fact there were some disagreements about whether or not there should be two teams involved. But, that's something that I had a hand in. In any event, this discovery of what now is called dark energy, the expansion of the universe, the source of that energy of which we do not yet know, was worthy of a Nobel Prize. So, interesting. I said I wanted to introduce three concepts. This is the third. Now, we've talked about two. Look back time, right? You're looking back into the past. Expansion, and what happens, what conclusions you come to if you project back in time. Third concept is one that results from Einstein's theory of general relativity. So this is a little harder to explain, but I think we can make it simple for you. And that is, Einstein, surprisingly, because this was not expected, demonstrated that light could be bent basically by mass. And that is because mass warps space-time. You've heard that, I'm sure, but I cannot give you what I feel comfortable with in describing it, how this warping occurs. But the fact is, it is true, it has been verified observationally now, that if you take light and you pass it by an object with mass, it will actually deflect the light path of the object. And this, it turns out, it's a very small effect, and it was confirmed actually in a famous solar eclipse experiment exactly 100 years ago. We celebrated that this year, the anniversary of that. So what happens is, if you're looking at a distant object, and you happen to be looking through a massive configuration, say a cluster of galaxies, what happens is that the light from that distant object will be deviated such that it will enter your eyes or our telescope out of focus, and in a way in which it is, you see a bunch of arcs. And so this produces some really beautiful pictures. And so it's just, on one hand, it's an interesting phenomenon, right? You take a picture here of a galaxy, and these are actual Hubble images. Here is a massive galaxy, and around it you see this object, this series of arcs of a totally different color, so they have nothing to do with this. And basically what we are seeing is out of focus images here that are produced by light from this more distant object that is being aberrated and producing these series of arcs. So actually we're seeing here three images of the same thing. This blob here is basically an out of focus image that corresponds to this and this. And so there are two important consequences of this. This effect of a gravitational lens enables us to see objects that otherwise would be too faint to see, because in fact it brightens, it takes that light and actually brings it to you, which otherwise would not happen. And so it enables us to see fainter objects further back in time than otherwise would be the case. And the second thing, which is even more important, is that these arcs and the amount of the deviation here enable us to determine the mass of that object. And what's really interesting, here you see a really beautiful arc, you know. So some of the neatest pictures are produced by this Einsteinian effect. In any event, so the fact that a mass is a very important parameter, right? Whether we're talking about humans, you know, or whatever, and it's an intrinsic property of any object that we want to study. It's one of those basic things that determines the more general properties of the system. And so if we want to understand the nature of objects out there that we can't touch, or we can only study because we see their light, this is an interesting way of determining their mass. Now, here is an interesting photo. This is a montage taken with the Hubble, where there's a bunch of galaxies that you see here, a whole slew of them, forget for a moment this wispy out of focus stuff, because that's going to be something else that I'll mention in a second. If you'll see here a bunch of arcs, there are actually more than 100. Here's an arc, I've got some arrows here. And basically, there's a nice arc right there, and there's one over here. If you study all of these arcs, it turns out we can determine what the mass distribution of this cluster of galaxies is. Now, we know from the brightness of each one of these galaxies what their masses should be, because we understand a lot of things about stars, like our sun. And so when we know how luminous, how bright it is, we know what its mass is. We can determine the mass of the sun very, very accurately from planetary orbits. And there is a great discrepancy. That is, if we actually add up the masses that we believe are in this image of all these galaxies from the brightness of the galaxies, and we compare it from the masses that we deduce based on the distortion of these 100 arcs, we find that there is a discrepancy by a factor of 10. There is 10 times more mass here that we do not see than we see. And that is basically mapped out in this, out of focus, diffuse, glowing material there. Since that mass does not produce radiation, we call it dark matter. And you've no doubt heard of dark matter. The fact is, Hubble studies of clusters of galaxies have shown that generally, when you look at any galaxy almost, and any cluster of galaxies, there is much more mass there than we can see. And it has given rise to this dictum that 75% of the universe consists of material that doesn't interact with radiation. We don't see it. And so it's basically governed by what we call dark matter. Now, the concept of dark matter itself is not that unusual. If you've ever heard of neutrinos, right, the little things that come from radioactive decay, that's dark matter. It does not emit or absorb light. So the concept that there exists dark matter is not unusual. What is unusual is that it is the predominant source of mass in the universe, and we don't know what it is. All right. Let me end by saying something about details of what galaxy evolution really gives us from observations. Because this is one of the triumphs of Hubble Space Telescope. When the telescope was launched, astronomers realized that it'd be nice if we could look out as far as possible to actually see galaxies at different universal times. What I didn't mention there was in the analysis of the so-called expansion velocity, the so-called Hubble constant, that led to the Nobel Prize, the age of the Big Bang, the time, look-back time to the Big Bang, turned out to be 14 billion years. So when we were able to finally determine exactly what the expansion rate of the universe was, it turns out Big Bang took place 14 billion years ago. So maximum look-back time for us to try to actually see the Big Bang, if we could, which we cannot with present instruments, is because of this hot fog. This hot fog enables us to see within 400,000 years of the Big Bang. So out of 14 billion, we can see all 14 billion minus 400,000. So we get to the hot fog, and that's it at the present time. When Hubble was launched, the largest look-back times from ground-based telescopes was about 3 or 4 gigayears or billion years. That is, we were able to look out about 3.5 billion of the 14. And so one of the early observing projects with the Hubble was looking at very distant galaxies to see what they looked like compared with those of the modern epoch. And there were two programs that you see here that showed what Hubble initially observed. One program that looked at objects out to 3 billion light years, which was about as good as ground-based telescopes could do, but they didn't give the sharp images that the Hubble did. And you can see, well, some interesting structures here that do not look like galaxies of the current epoch, in fact, which appear here. So those of you who have an interest in astronomy realize that most galaxies nowadays tend to be symmetrical and either of a spiral shape or perhaps this elliptical amorphous shape. But they're fairly symmetrical. When you look at galaxies that are 3 billion years old, you see something like normal galaxies of the current epoch. That is, you have a nucleus here and you have a couple of spiral arms. But you get a lot of strange beasts, ones with a double nuclei. I'm not at the best place to, let's see. There's some here that show that. Very asymmetrical. Well, there's two kind of hot spots. So these galaxies, and this is at a distance look-back time of 4 billion light years, don't show this nice symmetrical structure. So, looked like evolution, we were